Welcome back to part 2 of our lesson on disconnecting means. In this section, we are going to look at the PV system disconnect. Article 690.13 PV system disconnect refers back to Article 100 definition of a PV system, which is components, circuits, and equipment up to and including the PV system disconnecting means. So what does that mean? Well, we have to refer to Article 690. There are diagrams at the beginning which show very simple drawings like we see at the bottom here that identify where the PV system disconnect is located. Now, the PV system disconnect is the device that isolates the PV system from everything else. Now, the important thing to know here, and this is really important, especially if you are talking to code officials like your inspector or your AHJ, you need to know where the PV system disconnect is, because that delineates the things that are covered by Article 690, the PV system, and everything else. If the thing that you're discussing with your inspector is not part of the PV system, then the requirements of Article 690, rapid shutdown for example, will not apply if it is not part of the PV system. In this example, we see the diagram for an interactive system, which we here at SEI call a grid direct system. You've got your PV array on the left, your inverter, and then a PV system disconnect on the inverter output circuit. It's pretty straightforward. It's usually that last disconnect either before or at the point of interconnection. Now, no other systems, conductors, parts, or pieces can be in the PV system. We can't mix things that are not part of the PV system in, say, a gutter that is part of the PV system. You can't run circuits for a lighting load through that gutter if that is part of the PV system and on the PV side of the PV system disconnect. So that is really the delineation of where the PV system is versus everything else. Now, Article 690.1b has all those different diagrams for different types of systems. The interactive system, as we see here, AC coupled systems, which we'll see in another slide here in a minute, DC coupled systems. And really, the important thing to know again is that this PV system disconnect is the point where the PV system ends. So anything outside of that PV system disconnect is not part of the PV system. Article 690 would not apply to those parts. The location of the PV system disconnect is going to vary depending on what type of system you have. Here, this is an AC disconnect. In a DC coupled system, that disconnect would be a DC disconnect for the PV system. So really pay attention to what type of system you have and clearly identify where the PV system disconnect is. So in most cases, the PV system disconnect will be an AC switch, except standalone DC systems. Obviously, there's no AC in a standalone DC system, so that PV system disconnect is going to be a DC disconnect. DC coupled systems that have batteries with them, that's going to be a DC disconnect. The disconnect will usually be between the charge controller and the DC bus, where the charge controller connects to the inverter and the batteries. So in that case, the PV system disconnect would be a DC disconnect. Now here we see a diagram of an AC coupled system. At the top portion here, this is our PV array connected to a standard grid direct interactive inverter. On the inverter output circuit, we would have the PV system disconnect. This would connect to a point which is not shown in this diagram, but this would be your backed up loads panel. This arrow would go to your loads. This connection goes to your multi-mode inverter. So this panel is isolated from the rest of the loads in the house by this multi-mode inverter. Multi-mode inverter, the energy storage system, your batteries, these are not part of the PV system. The PV system disconnect here on the inverter output circuit for the grid direct inverter, that delineates where the PV system starts and ends. So anything to the left of this PV system disconnect is part of the PV system covered under Article 690. Anything on the right of that, all this load center down here, the multi-mode inverter, the energy storage system, the point of interconnection for the interactive system, those are not part of the PV system. They would be covered by other articles in the National Electrical Code, not Article 690. So things like I mentioned before, rapid shutdown does not apply to battery systems because that is not part of the PV system. So Article 690 does not cover energy storage systems. That was all removed from Article 690 and moved to a different place in the code. So we don't have to do rapid shutdown on energy storage systems. Other things in Article 690 would not apply to that part of the system. Now, Article 690.13a has different requirements for the location of our PV system disconnect. Now, let's keep in mind that we are specifically talking about the PV system disconnect, which may also serve as an equipment disconnect for the inverter, but not necessarily. So these requirements that we're going to talk about in this section specifically apply to the PV system disconnect. Must be readily accessible. You can't put it on the roof underneath the array. You can't put it in an attic that doesn't have a stairway leading up to it to be easily accessed. It has to be somewhere that you can get to. For systems over 30 volts, which is every system that we're going to be installed, pretty much, very rarely would we have a system less than 30 volts. If it is readily accessible, which we already identified that it must be readily accessible, and it has a door or a hinge cover that exposes live parts, it must be locked shut or require a tool to open. Here we show an example where we put a little padlock on the little tab that prevents that cover from being opened. I had a really good experience using padlock devices, which are the little plastic locks that utilities use to lock the meter can. You can buy those online. You can get 1,000 of them for less than 20 cents for the little plastic locks. You can even buy them custom with your company's logo on them. They work really well to lock that shut without having to go and buy an actual padlock. We want to refer to Article 690.1b to figure out where the location of our PV system disconnect is for the specific system type that we are going to be installing. Now, marking our system, we have to use a disconnect for our PV system disconnect that will clearly indicate whether the disconnect is open or off or closed on. Now, the disconnect switches with the big lever, that clearly indicates whether it's on or off. Typically, this indication is going to be provided by the manufacturer. In most cases, it's going to be the big switch with the lever. That's easy enough, indicates whether it's on or off. The disconnect needs to be labeled PV system disconnect, and there may be some additional markings that we can put on that. If it also serves as the equipment disconnect, we may have some other information about the system on that disconnect as well, and we'll talk more about that in the labeling lesson. If the line and the load terminals are both going to be energized when the disconnect is off or open, we have to mark it with this warning label that says electric shock hazard, terminals on line and load side may be energized in the open position. We'll talk more about this in the labeling lesson, but the important thing to know here is that we only need this warning label if both the line and the load terminals may be energized when the disconnect is off. On the AC side, in most cases, that will not be applicable because the line and the load side will not both be energized. As soon as you turn that disconnect off, if it's an AC disconnect, the inverter will shut down because it's lost utility power. The utility side of that disconnect will still be energized, but the load or inverter side of the disconnect will not because there are no capacitors on the AC side. There's no output on the AC side of that disconnect. We would not need that label. Now, if the PV system disconnect is on the DC side of the system, say a DC coupled multi-mode system where you've got a charge controller, that would be both energized on the line and the load side, because when we shut that disconnect off, the load side is still being energized by the PV array, and the line side is still being energized by the battery bank. So in that case, we would need to put this warning sticker on that PV system disconnect. There are some other requirements for PV system disconnects. We can have no more than 6 switches for PV system disconnecting means. Now, we can use a single disconnect for multiple inverters, and a good example of that is an AC combiner panel. We could have a bunch of inverters like we see in the picture in the bottom right-hand side there. That is a load center. We've got a bunch of different breakers in there. Each one of those breakers is connected to an inverter. The output of this load center would have a single disconnect to it, so that would be our PV system disconnect. So we could have 8, 10, 20, 1,000 inverters all connected to a single disconnect. That would be our PV system disconnect. We can have multiple PV system disconnects, up to 6, if we have different arrays in different parts of a commercial building, for example. We could have microinverters or AC modules on a single circuit that might have 1 PV system disconnect, could have up to 6. That's allowable under the code. There's an informational note in this code section that says that the number of PV system disconnects does not limit the actual number of PV systems. They just can't have more than 6 PV system disconnecting means on one site. So one single dedicated breaker could disconnect several different PV systems across, multiple roofs of a building. That's completely acceptable as long as there are not more than 6 PV system disconnects. Doesn't mean we can't have more than 6 disconnecting means. Those can be separate things. Article 690.13d has some requirements for the rating of our PV system disconnect. It has to be rated equal to or greater than our maximum circuit current, obviously. We wouldn't want a disconnecting means that would be rated less than our circuit current, or we might damage that piece of equipment. It has to be rated for the available fault current, or the ampere interrupting capacity, AIC, of that circuit. We would need to look at the circuit and determine what is the available fault current coming from our primary power source, typically the utility, and make sure that we have a disconnect that can meet that fault current rating. Has to be rated for the system voltage. Also pretty obvious, we can't use a 240 volt AC disconnect on a 600 volt DC circuit. Get the right disconnecting means for the circuit that you're going to be installing it in. So here we've got a panel with a main breaker in it. If we zoom in on that label, we can see that this is rated for 1200 amps max, 600 volts AC. We don't have the AIC rating here. We would have to dig into that label a little more closely. We might have to bring up the user manual and see what that is rated for. If this was an AC combiner panel, which in all honesty I don't think it is, I think this is a load center, but let's just say this was an inverter combiner panel, that main disconnect, if this was an AC combiner panel, could be the PV system disconnecting means. We would have to label that breaker as such. Obviously, we can switch it back and forth. We can visibly see if that is on or off. That's pretty straightforward. We could probably lock this cover, so we could lock it in the off position if needed. Now 690.13e has some different requirements for what is allowed to be a type of disconnect. We must have a disconnect that can shut off all the non-solidly grounded PV system wiring and disconnect it from all other wiring systems. So in the AC side, obviously that's going to be the hot ungrounded conductors. We don't break the solidly grounded neutral conductor. The DC side, if this was a DC disconnect for the PV system disconnect, we would break the ungrounded conductors and the functionally grounded conductor if there was one in the system. There's not usually solidly grounded conductors on the DC sides of our systems, and obviously we do not break the equipment grounding conductors. Must be lockable in the off position per 110.25. So we could have a switch with the lever handle. All those switches, when you turn the lever down, there's a hole in the lever and a hole on the switch box, and you can put a lock through that to lock it off. Oftentimes enclosures, like we saw in the last slide, if we shut that main disconnect, which would be our PV system disconnect, off, we can close the cover, and there should be some means of locking that cover closed if we had to, or if it was remotely operated, that would lock that out. There are several different types of disconnects that we can use. A manually operated switch or breaker, that's pretty obvious, standard equipment that we use in our systems. Connectors meeting the requirements of 690.33D1 or D3. So if we pull our code books out and look at that section, D1 says rated for interrupting current without hazard to the operator. So that would be some type of either disconnect or connector that's rated to interrupt the current without harming the operator and hopefully without damaging the equipment itself. D3 says supplied as part of listed equipment and used in accordance with the instructions provided with that listed connected equipment. So again, that could be a connector, say in a microinverter branch circuit, that is rated to interrupt the current of that circuit. Could also be a pull-out switch with the required interrupting rating. Could be a locally operable and or remote controlled switch circuit breaker. So we'll see a picture of that towards the end of this presentation. The caveat with that is that if it is a remote controlled switch, if the control power is interrupted, the switch must automatically turn off or open. That's part of those requirements. And then you've got 5, which is kind of everything else. And that means a device that's listed or approved for its intended application. That allows manufacturers to use different pieces of equipment that they specifically have listed as a PV system disconnect. It allows the industry to have other options available in the future if somebody comes up with some really interesting device that could be used as a PV system disconnect, as long as it's listed and approved for that intended application. Obviously, you've got to read the manual and install it and use it per the manufacturer's instructions. Now this section also has a little informational note that says circuit breakers marked line and load may not be suitable for backfed or reverse current. So what that means is if you have a breaker that is specifically marked line and load, which most breakers are not, you do see this on the larger commercial breakers, they may or may not be suitable for backfeeding. You would have to check with the manufacturer and see what it was designed for and if it is capable of backfeeding. Some are. You just need to check with the manufacturer and make sure that it is being used as intended. Now let's talk about 705.20. Just a refresher, Article 705 is interconnected electrical power production sources. So this has the requirements for our point of interconnection. These requirements are basically going to be almost exactly the same as what we just talked about with the PV system disconnect requirements from Article 690. So it must disconnect the source output circuits, our inverter output circuits in most cases, from conductors of other systems. Pretty straightforward. We've really kind of talked about that. The types of disconnecting means we're allowed are the same as 690.13e, which we just talked about in the last slide. Simultaneously disconnects all ungrounded conductors in the circuit. We discussed that. Pretty straightforward, readily accessible. Obviously, we need to be able to get to it. Externally operable without exposure to live parts. So you can't have to disassemble the box in order to get to the disconnect. That's kind of common sense. Requires a tool to open or it is lockable. Clearly indicates on or off and has sufficient ratings for the circuit. I mean, really, you should never be installing something that doesn't have sufficient ratings for the circuit. That's pretty common sense. And it has to be marked per 690.13b if both the line and the load side are energized in the off position. That's the warning label that we talked about a couple slides ago. Primarily would be needed on the DC side of the system if you had a DC coupled system. Not usually needed on the AC side of the system, although you need to check with the inverter manual or the manufacturer to make sure that that is in fact the case, that when the disconnect is off, the AC output of the inverter is immediately stopped and there is no energizing on both the line and the load side. Now let's talk about what the requirements are if we are doing a supply side connection. So here we see a diagram of a supply side connection. We've got our point of interconnection at the top here, these little dots with the yellow outline there. That's our point of interconnection. Goes to our disconnect here. This would be both the PV system disconnect and it's our overcurrent protection device because it's got fuses in it there. The code says, and this is in Article 230.82.6, says we must have the disconnecting means listed as suitable for service equipment. So you can't just pull any disconnect off the shelf. It has to say suitable for service equipment. That means it's going to be rated for 60 amps or higher, has that listing for service equipment. If the fuses are not integrated into the disconnecting means, and really even if they are integrated to the disconnecting means, the disconnect must be on the service side of the fuses. That's what we see here in this diagram. You can see the conductors coming from the point of interconnection go into the disconnect, hit the actual physical disconnect first, and then go through the fuses. If the fuses were not integrated into the disconnect, they would need to be on the load side of the disconnect. So they would be in another piece of equipment below the disconnect switch in this diagram so that they would be isolated from the primary power source. Now, this is a pretty simple requirement, and it just means that when we shut that disconnect off, we are de-energizing those fuses so that we can service the fuses. We don't want to get in there and have to be pulling out fuses on the line side of that disconnect because part of those fuses would be energized and that would be a safety hazard. Now, this disconnect in the diagram that we see here can be the PV system disconnect, and it could serve as the equipment disconnect for the inverter. They can be the same thing. Obviously, we're talking about supply side in this slide, but if it was a load side connection and there was a circuit breaker, that could serve as our overcurrent protection device for the PV output circuit and as the PV system disconnect. Those devices can serve multiple purposes. Okay, that's the end of our discussion on PV system disconnects. In the next section, we're going to talk about equipment disconnecting means. That's the equipment that we use to disconnect the pieces of electronics that we may need to service. So take a break, join me in that part when you're ready. Thank you.